Okay, folks, this is Fukushima reactor number 2 with the 73 sievert per hour rate. I redone the calculations because I found a mistake in my last set of calculations. For some reason I had 788,400 and it was supposed to be 262,799. So I changed that, as you can tell, all the way through the equation, and it changes the amounts on the equation, but it didn't change the effectiveness of the equation. As you can tell, I did it the old-fashioned way, by hand. D was 578.16 times 10 to the third, which is in hundreds of thousands of sieverts after 30 years. It eventually tops out at see if I can get this on here right. There it is. 1.1415 times 10 to the sixth. That's this one right here. And then the iodine, that was the strontium, by the way. The iodine was 212 on the original first 8 days. Then by this date here, by 128 days, it had hit max. 424 sieverts per hour. So that's basically what it's saying. As you can tell, this right here is the sieverts per hour. I'm using the 73 on the 2011 time frame that was given to me by Seeker. The internet is overreacting about Fukushima radiation. Here is why. February 12th, 2017. I did that to show how the equations work when they're properly done. And from the looks of it, we're going to see a lot more sieverts come out of that strontium. But the iodine pretty much maxed out. Well, it did max out, actually. The equation started to equal the same thing, which means it maxed out. Which means in order to change the sieverts from iodine anymore, you have to go up here, and this 2.2 has to change. The 2.2 is the continuous output. So the output would have to go down in order for this equation, for this answer here to go down any further. And this one here isn't far from the top. It's like 1.1266 versus 1.1415. Both are 10 to the sixth. So as you can tell, they're getting really close to each other now. And that's at 180 years. At 30, that's the strontium. Well, I think that's pretty much it. You can check my calculations again. You've got your usual half-life, continuous output, your P, Y equals initial amount, X equals 1, 2, 3, 4 to Z. Z must equal Z units divided by P units as long as the P units is smaller. Whichever units is smaller is what you got to have this in. E, that funny looking E-like thing, is a summation, and the D is the amount remaining, which can also be your initial amount once you start the equations. Yep, that's pretty much that. Have a good one. And oh, one other thing. This definitely changes things in that it basically tells us that there's going to be a lot of radiation coming out. I've heard there was as much as 1 million sieverts initially from the initial time of the, shortly like a month or so after the explosion, which would be probably the case because you figure 216 of them when it came from the first 8 days after Fukushima started on the iodine. However, it went up to 318. It would have slowly went up over the next few days or a couple of weeks. Well, have a good one. Thomas Willis out.